So in the beginning of this class, we spent a lot of time on classification problems. And recently, we've been talking quite a bit about regression. What we're going to do today is to move on to another type of prediction problem, conditional probability estimation. So we'll start by looking at sources of uncertainty in prediction problems, and then we'll see how this uncertainty can be captured by linear functions. And eventually, this will lead to the logistic regression formulation. So here's a basic question. Suppose you want to build a classifier, and let's say you have all the training data you could possibly want. Okay, as much data as you like. Can you, in general, hope to get a perfect classifier? The answer, sadly, is in general, no. And there are two big reasons for this. The first reason is that the features you have, the x, may simply not contain enough information to perfectly predict y. Okay, so for example, let's say that the data, the x, are medical records for patients who are at risk for a certain disease. Okay? And let's say y is whether the patient actually does get that disease over the, say, next 5 years. So even with all this information, even with the complete medical record, it's still not possible to predict with complete certainty whether or not somebody is going to fall sick. There's so much that depends on chance. So this is a situation in which we would like to be able to make a prediction, but it would also be useful if we could accompany that prediction with some sort of quantification of the uncertainty. If we could say something like, there is an 80% chance that this person will fall sick. Now, the second big reason why in general we can't hope for a perfect classifier is that very often the kind of classifier that we're using is simply not capable of perfectly capturing the true decision boundary. Okay, so let's look at this picture over here. We have a two-dimensional situation, okay? There are two classes, purple and green, and there is some true decision boundary between the two classes. But let's say we're using linear classifiers. There's no way to perfectly capture this boundary. The best we could do would probably be something like this. Okay? So in this case, we would still be able to make predictions, but it would be nice if we could also quantify the uncertainty. You know, if we could say something like, there is a 70% chance that the label is green. So we're talking about situations in which we want to classify, but in addition, we also want to output a probability. We want to output the probabilities of the different labels. Now, for simplicity, we're going to be looking at the case where there are just two possible labels, plus and minus, +1 and -1. Okay, this is the binary case. The methods that we develop, the logistic regression method, applies also in the multi-class setting. And we'll see how this generalization works. It's very easy, but we won't see it for another week or two. Okay, so for the time being, we're looking at binary problems. And we have points x, and we want to be able to predict the probability that y equals 1 at x. Okay? Now, of course, the probability that y equals -1 is just 1 minus this. Now, let's see what happens in the picture we looked at before. Okay? And let's say that we want to use a linear function. Okay, so we'd have a boundary like this. Let's see. And along the boundary, there is a 50% chance that y is 1. Okay, let's say in this case that green is +1 and purple is -1. So along that line, there's a 50% chance, say, that y equals 1. And then we'll look at parallel lines. So along this line, the chance would be slightly higher, let's say 60%. And along this line, the chance would be slightly lower. The probability of y equals 1 might be something like 40% along that line. Okay, so this is the kind of model that we'll be coming up with. We'll have a linear decision boundary. On one side of the boundary, we'll predict plus. On the other side, we'll predict minus. And in terms of the probabilities, it really depends on the distance to the boundary. The closer to the boundary, the closer the probability is to a half. Now let's see how this would work out mathematically. So let me go ahead and draw a 2D grid. Okay, so let's say we have two dimensions like this. Okay, this is 0, 1, 2, 3, 4, 5. And along the x, so this is the x1 direction, and then we have the x2 direction, and along this direction we have 1, 2, 3, 4, and 5. Okay, so we have two-dimensional data, okay? And let me draw a linear boundary. What about this boundary over here? Okay, what is the equation of this line? Well, let's see, the equation of the line is basically x1 plus x2 equals 2. Okay, that's the equation of that line over there. Let's write it in a slightly different way. Okay, let's write it as x1 plus x2 minus 2 equals 0. Okay, and in general, we're going to be writing our linear boundaries like this, as some linear function equals 0. Okay, so this is the linear function in our case, and the boundary is when this linear function equals 0. Okay, now on one side of the boundary we'll predict plus, on the other side of the boundary we will predict minus. What is the set of points along which we are going to predict, say, a 60% chance of plus? Okay, it might be something like this. Okay, what is the equation of that line? Well, let's see. That line is x1 plus x2 equals 3. And another way to write it is that x1 plus x2 minus 2, which is our linear function, equals 1. Okay? And now let's look at a line on the other side, maybe something like this. If these are the 50% points, where there's a 50-50 chance of the two labels, and these are the 60% points, where the probability of y equals 1 is 60%, then this symmetric line on the other side will be the 40% points, where the probability that y equals 1 is 40%, and conversely, the probability that y equals minus 1 is 60%. And what's the equation of this line? Well, this is x1 plus x2 minus 2 equals negative 1. So do you see the general pattern over here? In order to classify a point, and in order to determine the probability that y equals 1, all we're going to do is to compute this linear function. In this case, x1 plus x2 minus 2. If it works out to 0, there's a 50-50 chance. If it's positive, then the chance is greater than a half. If it's negative, the chance is less than a half. Okay? And the larger this value, the larger the probability that y equals 1. Okay. So now let's move to a more general setting where we have d-dimensional data. Okay. And again, we're going to be computing some linear function of this data. Okay, so we have data points x in Rd. What is a general linear function in d dimensions? Well, it's something of this form. w1x1 plus w2x2 all the way to w2xt plus this extra intercept term b. Okay, so this is a general linear function. And we can rewrite it a little bit more compactly as w dot x plus b, where w is just the vector of all the coefficients w1 through wd. Okay, so that's our linear function. So we get a point x, we compute this linear function. If it turns out to 0, that means that this point is right on the boundary between the two classes. There's a 50-50 chance that y equals 1. And the larger this function is, the larger the probability that y equals 1. But how do we get an actual probability out of this? After all, this function, w dot x plus b, this returns an arbitrary real value. It could be anywhere from minus infinity to plus infinity. How do we convert this into a probability? How do we take a number from minus infinity to plus infinity and get a number in the range 0 to 1? The way we do that is by using the squashing function. Okay? So the squashing function takes a real value, z, and it outputs 1 over 1 plus e to the minus z. And this is something that's always in the range 0 to 1. Okay, so in this graph, this is the z over here. And on this axis, you have s of z. So when you plug in z equals 0, for instance, into that formula, you get back a half. So you get that point over there. And as z gets larger, the numbers get larger as well. And as z goes to infinity, they asymptotically reach 1. That's what you're seeing up here. And when z goes to negative infinity, they asymptotically reach 0. So this takes a real number, turns it into a probability, and when you plug in the value 0, you get a half. So this is really exactly what we need. Okay. So when we have a point x, the probability that y equals 1 is going to be the following. First, we compute the linear function, w dot x plus b, and then we put it through the squashing function. And this gives us a probability in the range 0 to 1. Now, this is the probability that y equals 1 for that specific point x. What is the probability that y equals minus 1? Well, it's just 1 minus this. Okay, so let's write that down. The probability that y equals minus 1 is 1 minus whatever we have up there, which is 1 minus 1 over 1 plus e to the negative w dot x plus b. Okay. Let's simplify it a little bit. Okay, so we get e to the negative w dot x plus b over 1 plus e to the negative w dot x plus b. And you know what? Let's multiply the numerator and denominator by exactly the same quantity, which is e to the w dot x plus b. Okay, so let's multiply top and bottom by the same thing. And what do we get? Well, the top just becomes 1. And the bottom becomes 1 plus e to the w dot x plus b. Okay, so we've simplified it a little bit. But now if you look at the two formulas, okay, so the one at the bottom is the probability that y equals minus 1 given x. If you look at this formula, and you look at the one up there, you see that they're actually very similar. And in fact, we can put them together and just have a single unified formula. Okay, what is that? It's the following. The probability of any y given x, where y is either plus 1 or minus 1, is simply 1 over 1 plus e to the negative y times w dot x plus b. So if you plug in y equals 1, you get the formula on the top. If you plug in y equals negative 1, you get this formula over here. And so now we have a single formula that covers both cases. This is the logistic regression model. So here's a summary of what we have. We have data in d-dimensional space. There are two possible labels. And in addition to classifying, we're going to output probabilities. And this is the form of the probability function. Now, it's based on two parameters, w and b, that define a linear function. What are these parameters? How do we set them? Well, this is what we have to learn from data. And we'll see how to do that next time. Okay? So that's it for today. We've talked a little bit about quantifying the uncertainty in prediction. And we've seen that this can be done quite easily using linear functions. Next time, we'll see how to learn this linear function. So see you then.